So I will introduce our next speaker. So he's from Czech Republic. His name is Mr. Dušan Kováčik.
Yeah,
He's
you are right.
an associate professor at the Masaryk University in Brno. And he's an expert for the plasma treatment of different surfaces. And his topic today is large area atmospheric plasma surface processing of PVB and Ionoplast interlayers for performance improvements of laminated glass. So I think it's mainly about to improve the adhesion and robustness of the adhesion. So please, Dušan, the stage is yours.
Okay.
Please welcome Mr. Dušan.
Thank you, Mr. Chairman, for introduction. Good afternoon, ladies and gentlemen. At first, I would like to express my thanks organizers for giving me an opportunity to have a talk on this Glass Performance Days conference. Even when I'm not working in glass processing technologies, and as it was told, I'm dealing and focus on plasma technologies. But I would like to introduce you in my presentation our own plasma technology, which we believe have or has potential for application for surface treatment, not only polymer films or PVB or Ionoplast interlayers, which can be used for laminated glasses, but also for float large area glass. Maybe at the beginning, I would like only introduce our center. I came from CPLAN Center. CPLAN is acronym for Research and Development Center for Plasma and Nanotechnology Surface Modification, which is a part of Department of Physical Electronics at Faculty of Science in Brno, in Czech Republic. Brno is about 200 kilometers far away from Prague, as you can see on this map. CPLAN was established in 2010, and we can say that it is leading Central European research and development institution in the field of inline plasma surface treatment. So it means that we are focusing on plasma technologies which have potential to be implemented directly in the production lines for different applications. Since 2019, CPLAN is large research infrastructure, so it means that we offer training and education of both academic and industrial researchers in our open access facilities and innovation laboratories. It means that in our laboratories, we try to optimize different plasma technologies, and if it is possible, we try to make also the transfer of these technologies to the practice. You are experts in laminated glass products, but I would like to demonstrate the potential of our technology just on these products, because we successfully finished the project last year in collaboration with two companies from the Czech Republic, and it was focused on enhancement of adhesion properties of laminated safety glasses using plasma. So it means that laminated glasses are consisting from two or more glass plates which are separated by interlayers, and adhesion must be very good in these products. For several decades, PVB films have been used the most commonly interlayer in these laminated safety glasses for common design, but as it was also mentioned, in modern functional buildings are increasingly used these safety laminated glasses as a load bearing, and in such a case, PVB is usually, or there is a trend to replace it by Ionoplast. This interlayer is more suitable due to its several times higher strength, up to 100 times greater toughness, and considerably higher stability under prolonged load and higher temperatures. Here is on this picture, you can see the real photo of the Ionoplast SentryGlas, which we used in our experiments in the premises of our industrial partner in Czech Republic. And our challenge was that Ionoplast interlayer have a very different chemistry than PVB, which requires slightly modified processing compared to PVB. The lamination must be when it is done on the thin side. As you know, in such a case, the problem we don't have problem, but the problem is when we want to laminate with air side. In such a case, we need, for example, to use the primers. So here on these pictures, you can see the primers which was used for the flowed glass and spread on the surface. To this, also from the environmental point of view, there is a question and challenge if some other technology could replace the usage of these primers. And we were motivated by our preliminary results focused on the adhesion properties of different materials. And we tested a plasma for activation, not only flowed glass, but also SentryGlas and also PVB. So we can say that plasma is a possible alternative method for leading to an increase in the adhesion of the Ionoplast interlayer to the air side, as I mentioned, without the use of the primer. And what is very important is that in such a case we should use the plasma which is generated mainly at atmospheric pressure. Maybe you are familiar with the plasma, but I can very briefly introduce that under the term of plasma we consider a quasi-neutral ionized gas with collective behavior, and this is highly reactive environment. So it means that it consists from electrons, ions, neutral atoms and gas molecules, free radicals and photons of UV radiation, for example. So this mixture of the particles can be used for surface modifications of the materials, can induce plasma chemical processes. Also, it is important to realize that plasma could have different properties. It is mainly generated by plasma discharges, as you can see on this picture on the left side. And if the temperature of very light particles, electron, is much higher than temperature of ion or gas, we are talking about the non-isothermal or non-equilibrium plasma. Such a plasma is good for the surface treatment also of thermal sensitive materials. Isothermal plasma is the plasma where these temperatures equals. Plasma can be used for different purposes, but if we are talking about the surface modification, what can plasma influence is the change in surface energy. We can change wettability, we can activate the surface or make functionalization. If we generate plasma in ambient air, we predominantly form polar groups on the surface like carbonyl, carboxyl, hydroperoxide, hydroxyl, or amino. But using the plasma, we can also change the roughness, and we can talk about the morphological changes. Using our systems, we are using gentle plasma. So in such a case, as I will show you, we don't suppose the changes in the roughness. Why it is interesting to use the plasma? Using plasma, we can change very thin layer on the surface. So it takes place in extremely thin region, about 10 nanometers. It is usually very fast. We can consider potential benefits, including minimal waste and control of surface functionality. And what is important, we can control plasma treatment parameters very easily. We can change exposure time, input power, supplying voltage, working gas, and so on. When I want to talk about laminated glass, we also, within our project, treated the flowed glass, but this is the topic of presentation of my colleague, which will start immediately after my presentation in the section product and process case studies, and will be given by my colleague, Dr. Krumpolec. He will focus in his presentation on activation of the glass. Yeah, if we want to treat the interlayer, polymer interlayer and atmospheric pressure, we have to find good and suitable plasma source. And it is not so simple, because it is possible to find different commercial plasma systems, but as you can see, they mainly generating limited volume of the plasma. They are using flowing gas for stabilization, or they are not sufficient homogeneous, as you can see in this case of gliding arc. For treatment of polymer films and also maybe PVB or Ionoplast, we can consider standard volume DBD discharge, which is used for decades for the treatment of films, and it is also in technical literature called industrial corona. But this system or this discharge has several disadvantages, like stability of the treatment, limited thickness of the material, and so on. So I would like to introduce our own technology, which is based on so-called diffuse coplanar surface barrier discharge. And as you can see, we are able to generate macroscopically homogeneous plasma without any stabilization by flowing gas. Yes, so we generate the plasma in very thin layer. It is about 0.3 millimeters, so film must be treated in this distance. We generate plasma with very high power density, reaching 100 watts per cubic centimeter, what means very short exposure times. Our plasma is of non-isothermal type. And what is important, system can be operating in dusty and humid environment without any risk of overcoming on transition to the spark or arc. System is robust, easily integrable into industry lines. So main advantage to the other atmospheric pressure system is that we generate quite large area, 20 centimeters, 8 centimeters, using one plasma unit, macroscopically homogeneous plasma. If we compare our system to already mentioned corona, we can see several advantages, like more stable treatment, and also higher efficiency of the treatment. So this is the corona, and under this corona picture we can see our coplanar discharge. Experimentally, in our laboratory, we investigated experimentally the plasma treatment of Ionoplast. Interlayer, we use SentryGlas with a thickness 0.89 millimeters. As a working gas, we used ambient air. Input power was 400 watts. We kept the sample in distance 0.3 millimeter, and exposure times, as you can see, were really very short, from 1 second to 5 seconds. And alternatively, when we wanted to study overexposure, we used 20 seconds. We know that it is very important to store the Ionoplast at good conditions to prevent the humidity. So we investigated different samples which were stored in the air, stored in the desiccator cabinet, and stored in the vacuum bags. We investigated, as a simple method, water contact angle measurement. As you can see, it is an angle between interface between solid and liquid, and between liquid and gas phase. If this angle is lower than 90 degrees, we can consider material the more hydrophilic. It is higher hydrophilic. As you can see on our graphs, even after very short exposure time, in duration 1 second, we were able to reduce the contact angle significantly. And as the optimal treatment time, we consider 5 seconds. In this case, longer exposure time did not affect the results, because we observed saturation. We investigated also surface energy. In such a case, we were measuring water contact angle using more testing liquids, and we used the OMS model for calculating. We investigated smooth side of SentryGlas and rough side on the right side. And as you can see, surface energy consists from dispersed part and polar parts. And for all plasma treatment in duration 5 seconds, 10 and 20 seconds, we can see increasement of polar parts. So this is indication that using the plasma treatment, we are incorporating oxygen content or polar groups to the surface, and we confirm by XPS measurement when we study the chemical composition that they are mainly oxygen containing groups. The stability of the treatment is also sometimes questions, and we investigated the stability in duration of 1 week. And as you can see, during these first 7 days, we didn't observe minor changes in the wettability, and we also didn't expect a return of this value to the value of reference sample. Good wettability, lower contact angle, higher surface energy is quite good indicator of better adhesion. So we also investigated adhesion using tape peel test method under angle 180 degrees using testing tape. So we were measuring the force which is necessary to remove the tape from the SentryGlas. And on the graphs, we can see that after 1 second exposure time, we observe more than 2-fold increase in adhesion. So it is really, really short time. And it is also interesting that extending the exposure time did not affect its further increase. Also it is interesting, if you remember, I mentioned that optimal exposure time was 5 seconds for water contact angle measurement, but adhesion is complex problem. We can see that 1 second is quite sufficient from this point of view, and we observe the saturation. There's maybe some we investigated also the roughness, but using confocal microscope, and there are double pictures at magnification 5 and 10 times, and on both sides, smooth and roof. And we could not use atomic force microscopy because of roughness of this SentryGlas. And the results which we obtained showed us that there was no change in surface roughness. We didn't observe it even after longer treatment in the duration of 10 seconds. We investigated also the transparency of plasma-treated Ionoplast, and in visible light region we revealed no optical changes of the material. The company with which we collaborated also told us that this is not so important problem in lamination process, but we investigated it. Most even, we observed a slight better transparency of plasma-treated Ionoplast for sample which was stored in vacuum, as we can see on the graphs on the right side. So this was the overview of some experiments in laboratory, but we also tried to do the treatment directly at the industrial partner premises. So here you can see the real photo when we were preparing the glass beams in the length 4.5 meters. On this picture you can see the activation of glass with a thickness 8 millimeters by 1 hour plasma unit. You can see ear bearings which are here, and using them we are able to keep required distance 0.3 millimeters. On the bottom picture you can see the treatment of Ionoplast. This is the picture which was taken maybe sometimes in the middle of the project. For pendulum tests we need much larger samples, so it was necessary to scan with this plasma unit larger area, but as I conclude, our technology has potential to be scalable, very simple, so it is not problem to treat also larger samples. So this is whole laminated process. On the first picture you can see activated SentryGlas which was put on the first plate, covered with the second one, and now the edges of the SentryGlas are cut away. We investigated different thickness of the glasses from 2 millimeters up to 8 millimeters, and also different combination of the treatment. We compared using primer, we replaced primer by the plasma, we treated only glass, we treated glass and also the SentryGlas. This is the result of pendulum test. You can see on the last photo that for laminated glass which was prepared using plasma treatment glass and also SentryGlas, that after the test it was not possible to put the testing bolt through the glass, so it was successful. As an example of PVHB treatment, I can show you this results, the laminated safety glass. On the left side you can see the picture with cracks because of a drop bolt test. And on the left side, you can see that there is no observation of cracks. Both glasses and also PVB was treated by our plasma. Using bending test, we verified significant 60% growth of average break-in force. When only plasma was activated, the increase was 52%. I would like to conclude that, as you can see, our plasma technology is robust. It can be implemented in different plasma lines. It is very simple, scalable. If we need to enlarge the exposure time, we can use several plasma units in one row. If we need to treat wider materials, we can arrange the plasma units, for example, like in this reactor, it is for treatment of materials with a width 1 meter. So this technology is easily integrated in the production lines. And also we are at the faculty, but we have a spin-off company which can make some transfer from CPLAN to the industry. At the end, I would like to give my thanks to my colleagues, mainly Richard, who is present here on the conference, and our PhD student, as also Professor Černák, who is the head of our center. Thank you for your attention.